Some rules of probability. Probability notation. If E is an event, then P parentheses E represents the probability that event E occurs. It is read the probability of E. The complementation rule. For any event E, the probability of E equals 1 minus the probability not E. Pictorially, we have the box for our universe, our circle E, and then outside of E is your not E. Example, the distribution of BA degrees conferred by a local college is listed on the right by major. We have English with a frequency of 2073, Mathematics with a frequency of 2164, Chemistry 318, Physics 856, Liberal Arts 1358, Business 1676, Engineering 868, for a total of 9,313 students. What is the probability that a randomly selected degree is in engineering? Round your answer to 4 decimal places as needed. First, we need to write the probability of the event, P parentheses engineering. The frequency for engineering is 868. Our total is 9,313. So the setup for our problem is 868 divided by 9,313. Dividing, we get our final answer of 0.0932. Continuing with this example of BA degrees conferred by a local college, what is the probability that a randomly selected degree is not in physics? Round your answer to 4 decimal places as needed. Our setup, P parentheses not physics. We have 2 choices now to set up our problem. I can either add up the 6 numbers of the degrees that are not physics, or I can take 1 minus the frequency of physics, which is 856, divided by 9,313. I'm using the fact that the probability of physics plus the probability of not physics equals 1. So I am using 1 minus the probability the student's degree is physics to get my answer of 0.9081. The special addition rule. If event A and event B are mutually exclusive, then the probability A or B equals the probability A plus the probability B. Pictorially, I have a box for my universe. A or B have nothing in common, so I can just add the 2 probabilities. More generally, if events A, B, C, and so on are mutually exclusive, then the probability of A or B or C or so on equals the probability of A plus the probability of B plus the probability of C plus any other probabilities. Example, a card is drawn from a well-shuffled deck of 52 cards. So we have a picture of a deck of cards. I have the Ace of Spades, 2 of Spades, 3 of Spades, 4 of Spades, 5 of Spades, 6 of Spades, 7 of Spades, 8 of Spades, 9 of Spades, 10 of Spades, Jack of Spades, Queen of Spades, King of Spades. And those cards are black. Next, I have a line of red cards, Ace through King, but this time the suit is hearts. Then I have Ace through King, clubs, which is black. Then I have Ace through King of diamonds, which is red. And that makes a deck of 52 cards with 4 suits. What is the probability of drawing a face card or a 4? I begin by writing my probability, face card or 4. Then I look at my face cards. The face cards are the jacks, queens, and kings. So that's 12 out of 52. Now I want to look at my 4s. I have a 4 of spades, a 4 of hearts, a 4 of clubs, and a 4 of diamonds. So I want to add to that 4 out of 52. Drawing a face card and drawing a 4 are mutually exclusive events, so I can solve my problem by adding 12 plus 4 is 16, 16 over 52, which reduces to 4 and 13, or 0.3077. The general addition rule. If A and B are any two events, then the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Pictorially, we have a rectangle for the universe. I have my circle for A and my circle for B, and they intersect. Circle A is shaded, circle B is shaded, and where they intersect is shaded a little darker because they overlap. A and B is only the part where they overlap. A or B is all of the shaded area. All of A, all of B, but we only write what is in the intersection once. Example. A card is drawn from a well-shuffled deck of 52 cards. What is the probability of drawing a face card or a heart? We have 12 face cards, 4 jacks, 4 queens, 4 kings. We have 13 hearts. So setting up our problem, we start with the probability of a face card or a heart. The probability of a face card, 12 over 52. We add to that the probability of a heart, which is 13 out of 52. Now notice that we have 3 cards, the Jack of Hearts, the Queen of Hearts, the King of Hearts, that were counted both times. So we need to subtract our overlap, which is 3 over 52. That gives us a total of 22 divided by 52. Reduced is 11 divided by 26. Or in decimal form, 0.4231. Continuing with our example of a well-shuffled deck of 52 cards, what is the probability of drawing a red card or a 10? First we write the probability, red card or a 10. Our red cards are the diamonds, in the hearts, which is half of our deck, or 26 divided by 52. Our 10s, we have a 10 of spades, a 10 of hearts, a 10 of clubs, and a 10 of diamonds, which is 4 out of 52. Before I add those two together, I also need to subtract my overlap, which is the 10 of hearts and the 10 of diamonds. Since I have 2 cards that overlap, I want to subtract 2 over 52. That gives us a total of 28 over 52. Reduced, that's 7 divided by 13, or our decimal of 0.5385. Recapping, some rules of probability. The special addition rule says that if 2 events are mutually exclusive, I can just add the probability of A to the probability of B. The complementation rule says that if I have the probability of not A, I can find that by using 1 minus the probability of A. The general addition rule tells us if we're looking for the probability of A or B and they are not mutually exclusive, we have to take the probability of A, add to that the probability of B, but subtract the probability of A and B to get rid of overlap.